Machine learning models efficiency analysis for image classification problem. The successful application of neural networks to solve actual computer vision problems has led to the emergence of many new models of convolutional neural networks, CNN, and their various modifications used for image detection and classification in recent years. Many CNN models can be pre-trained, and the aim of the work is to ensure the efficiency of machine learning of modern convolutional neural networks by using different methods. So, the goals of the work are to develop a plan and set up a series of experiments on the application of widely used machine learning methods in relation to modern CNNs based on actual data. Evaluate the effectiveness of machine learning on free and frozen weights. Formulate recommendations on the practical application of machine learning techniques and methods. The dataset consists of a set of images of different birds. The dataset was taken from the Kaggle platform, and you can find the dataset by scanning the QR code. The dataset is constantly updated and the number of images is constantly increasing. You can see the number of 100 classes in the link, but now there is a version of the dataset with 400 classes. By the way, at the time of conducting the experiment, there were only 300 classes. The dataset is divided into 3 parts: train, validation, and test images of the same size. We have used the following metrics. The precision is the ratio of correctly classified images to all classified images. The recall is the ratio of correctly classified images to all relevant images. The F1 score is the harmonic mean of precision and recall. We have used the minimum and average metrics for each class. According to the goals of the work, we have selected EfficientNet V2 Type B0 and ResNet50 as the models to be evaluated, and decided to test them by 3 methods of training CNNs, including training the model from scratch, fine-tuning the pre-trained model, and transfer learning. We have used a Kaggle GPU as free and powerful computing power. This GPU has a memory of 16 gigabytes. This was the main restriction for processing only 128 images at once. The basic training procedure of each CNN was divided into 3 experiments, each containing a limitation of 100 epochs and a learning rate of 1e-4. The first experiment was used to train the model from scratch. The second experiment was used to fine-tune the pre-trained model by using the frozen weights, unfreezing them, and finishing training. The third experiment was used to transfer the pre-trained model to the new model. This slide is a summary of the ResNet results and timings of the experiments. You can see comparatively worse results of the scratch model by a few times evaluating the error rate. Even using bare transfer learning, the error rate is still higher than using fine-tuning. By the way, fine-tuning consumes a lot of time and is more complicated in the code. This slide is a summary of the EfficientNet results. The difference between the methods is almost negligible, but you can see that ResNet hasn't reached even 90% accuracy, but EfficientNet has reached more than 96%. You can see the time consumption of the fine-tuning experiment, which is 6 times slower than the bare transfer learning in this case. Summarizing all said, we can say the following. Firstly, we can still use random weights for some mediate efficiency if there is no pre-trained model. Secondly, we can obtain a pre-trained model, we can fine-tune it to achieve better results. And finally, we can use ResNet models in combination with other models to achieve better results. But if we need to use only one model, EfficientNet version 2 is a better choice. Thank you for your attention.